Today's key math talk is given by Professor Benoit Charbonneau. And
thank you, Mangshui. Well, thank you for the invitation. I appreciate that. It's been quite something to see my name in all the staircase for the past 2 days. At every floor as I climb, I see my name there, so it's a bit funny. Anyway, I want to tell you a story, and I've been called in to give the pure math prof talk, and I thought, now who here is actually in pure math right now, and who is not in pure math? Okay, that's good. Who's in applied math? Why are there so few of you? And then you can raise your hand like you're proud of it or something like that. So I want to tell you a little bit of an applied story from the point of view of a pure mathematician. So I have this friend. It's a very good friend of mine. He actually served me a breakfast a number of times while I was finishing my thesis. He was running very far to get croissant and had his own jam and cooked bacon. And then I would stop by his house, have breakfast on Sunday morning, and would keep biking to the university to finish my thesis. So it's a very good friend. One day he visited, and he's a soft matter scientist. He's a physicist, really. And one day he stopped at my office and said, "Benoit, do you know about spherical harmonics?" I said, "Sure, I know." And then he asked me a question. I'll tell you what that question is. And he comes from a very different perspective. So let me tell you from which perspective he comes from. So this is the physics definition. The physics definition, and that's in 3D, okay? That's physics definition of the spherical harmonics. So this is the spherical harmonics. And this P there is the Legendre polynomial. All right, so what is this horse? And as a physicist, what he does is he's going to plug this into Mathematica and play with it and do various things. And in a sense, for him, the spherical harmonics are not, there's these objects given by Wikipedia, basically. And that's pretty much it from his point of view. From my point of view, what is the spherical harmonic? So this is the math version. Well, this is very, very simple. I'm going to define a vector space, H sub L of Rn. It's going to be the set of all polynomials. So I'm going to choose right now to be with complex coefficient, though you could put real coefficient if you prefer. X is going to be shorthand for x1 to xn. That's coming from the Rn here. And I'm going to ask that this polynomial is homogeneous of degree L, and that it's harmonic. So that means that the Laplacian applied to it is equal to 0. What is this gadget here? It's the sum of the second partial derivatives. That is the space of spherical harmonics. That's from my point of view, that's what spherical harmonic is. What my friend was giving me here is a particular basis of, so this thing here, so HL of R3 is the span of this particular basis here, of QML with value of M starting at minus L and finishing at plus L. And you'd see here that from his point of view, you use here a very particular choice of coordinate on the sphere, which is just the spherical coordinate. There's no notion of radius here. you have to tweak this if you want to add the radius. And it turns out that they are called spherical harmonics because they correspond to, if you restrict them to the sphere, they are eigenvectors for the Laplacian on the sphere. So if you take P and HL of Rn, then P, restrict that function to the sphere of radius 1, and if you apply to that the, oh, I didn't prepare for that, sorry. I'm going to have to do R3, but otherwise I'll get the wrong answer here. And I don't want to lie since we're recorded. So this is what we get. So that's why they're called spherical harmonics. And of course that means something physical. I have no clue what it is, but my colleagues in chemistry that study the hydrogen atoms and things like that, for them that means something. But for me, they're just solution to a differential equation. I have a particular basis, so okay, what can we do with that? All right, so what his question was, and I'll call it the question in capital letter, is to find the equivalent to a particular expression I'm going to write down. That's the expression to WL of XYZ, which is the sum M1 plus M2 plus M3 equal to 0 of some weird symbols. And then I look at this, these bases that I just erased, which anyway you don't care about its exact form. I substitute 3 vectors here, or 3 points that are on the sphere. So here, x, y, z are on the sphere. So as a, I can write them, if you want, using the angle theta and phi that are part of spherical coordinates. Or I can just think of those functions as functions of the sphere, and I write them that. And you want to find this equivalent in higher dimension. Okay, so first natural question is, what is this beast? What are its properties? And it turns out that the reason this was interesting is when you're dealing with physics, you don't really care about the choice of coordinates. And therefore, the systems you're looking at are invariant on the rotations. And in fact, this function has this property. So the key property is that WL of Gx, Gy, is equal to WL of XYZ for all G in SO3. For all rotations, this is invariant. Okay. So the story I want to tell you is a story that, in a sense, is what I cannot tell you all the math I learned in trying to answer this question, but I can tell you a part of the math I learned, and then I'll close by saying that all of that what I learned was actually relevant. But this turned out to be the strategy that needed to be I should point out that the physicists already knew what was the equivalent in dimension 4. And their strategy to find it in dimension 4 was exactly the strategy I'm going to talk about right now. Exactly the same thing. And it is actually to use an atomic bomb to kill a fly. Roughly, that's what it was. So what do we do? So I need to detour a little bit and bring you to this idea of representation theory. And so what is representation? I want to talk about representations of groups. So I suspect that some of you are not familiar with this language, so let me mention what it is. So you take here a group, G a group. You take a vector space V. And a representation is a map, a group homomorphism from G to the endomorphisms of V. So it's a group homomorphism. That means that if I multiply two elements in the group and apply this function, I get two matrices if you want, or two endomorphisms. And it's the same thing of applying it on this side, and it's the same thing. It also respects the inversion. That's what a group homomorphism is. So this is a representation of group. Very often we'll just refer to this as V. And why is this important? Is that the space that I mentioned, HL of Rn, they are representations of the rotation group. In which way? It's very simple. These are functions that are defined on Rn, and what I could do is just precompose with rotation. And so that's what it is. So if f is one of those functions, then and g is a rotation, then g acts on f just by composing with G inverse. That's very simple. Okay, I told you earlier I don't want to lie because I'm on camera. I will lie. I always lie in front of an audience like this. That's part. Otherwise, you have to say too many things. So I'm going to hide a few things under the carpet, and I'm going to immediately stop talking about representations of group, and we'll pass to the tangent plane. I'll talk about representation of Lie algebras. So you can replace, and I'm not going to tell you how, this discussion of SO3 acting on HL of R3 by little SO3. What is a little SO3? I'll tell you in a few seconds. Acting on HL of R3. So this is the Lie algebra, and so what it is, it's the thing which are tangent to the identity of that group, and where simply they're 3 by 3 real matrices such that they are antisymmetric and that their trace is equal to 0. Very simple. I'll just show you very quickly why these two things are somewhat related. As a group, the group of rotation, that's if you wanted to see how much dimensions do I have. Well, just imagine you want to rotate the first vector and your standard basis to a given vector somewhere. That vector is a vector of length 1, and so you have basically a sphere of choice. So you have 2 dimensions. Let's say you want to rotate now the second vector to another vector which is perpendicular to the first one you chose. You have a circle of choice. And so you add 1 dimension. And then the last vector just gets carried along. So this group is a group of dimension 3. This space here is also a space of dimension 3. You can imagine if it's antisymmetric, that means only the upper entries matter, and you have 3 of those entries. It's also 3-dimensional. All right, it's 3-dimensional, so I'm going to replace SO3 by another Lie algebra, which is also 3-dimensional. And it's very much related to this. It's SL to R. And the reason I'm doing that is that this will be much simpler to play with everything. And it turns out that all of what I'm doing here is legit, and you can do that. I'm not going to tell you why, but it works. And so what is this space here? Was the space of all the 2 by 2 real matrices that have trace 0. And so this is very simply the span, the real span of maybe this matrix. I have this matrix has trace 0. I'm going to put another matrix 0, 0, 0, 1. And whoops. I'll put the 1 here, and I'll put the 1 there. And I'll call this matrix H, this matrix X, and this matrix Y. Okay, I didn't mess up. Excellent. So it's a Lie algebra. That means I have a bracket operation. So what is the bracket operation? It's just the anti-commutator, the commutator, sorry. So what happens is these are matrices. I can multiply them in one way or another. I take the difference. When I do that, I get that H with X is equal to 2X, right? That H with Y is equal to minus 2Y, and that XY is equal to H. That's the way this thing works. And I want to tell you about the representation theory for this Lie algebra. And I remind you that this Lie algebra, this representation theory is very much related to the representation theory of SO3, which is therefore related to the representation theory of SO3, the capital SO3. It works? I see some people doing the computation, so that's good. So here's a vector space I'm going to introduce. I'm going to call it V sub L. And V sub L will be the span, the complex span of these little gadgets. I'm going to do V x, little x. I want a little x this time. So I'm going to make it all funny like this. L plus k, I think. Okay. L plus k, y, L minus k. So I want you to think that x is basically the first vector in R2, and y is the second vector in R2. I could call them E1 and E2, but except I want to put indices later. And if I call them E1 and E2, then I'll need to have an E1 subindex something and an E2 subindex something. So it's just going to get too messy. So let's write it this way. And here I have k going from minus L to L. So this is a very particular basis of that space. And this is a representation of SO3. This is a representation of SL2. Maybe I'll call this gadget here little fk. And the reason I introduced this is that as a representation of SL2R, and in parentheses you can say SO3, and you can say big SO3, then HL of R3 is isomorphic to this VL, and FK, and in that isomorphism you have that this Q LM is mapped to a multiple. I'm not guaranteeing is that one, so let's just fake it and let's just use the same one. It's mapped to FM. Okay. So let me explain a little bit how this representation works. I'll do a little example here. Suppose I take an element like this one, little x squared y. So that would obviously be well, I don't know which fk it is, but it doesn't matter. And now let's suppose I apply capital X on that. Well, the way this works for representation of a Lie group is that you need to apply to each of the term in the multiplication one after another. So you'll do big X of little x times little xy plus little x, big X of little x times y plus little x squared, big X of little y. And now you go back to your matrices, which are here. So big X is sending little x to 0, and it's sending little y to little x. So this is 0, this is 0, and this is little x cubed. Does that make sense how this works? No, okay. Sorry?
If you x will y, then
Oh, I'm not saying this is one of those things. I'm just explaining how the action works. Okay? And the action works is if you have a polynomial like this and you want to apply one of those matrix, you have to apply it to each letter separately. And you add what you have there. And I was telling you little x, you should think of it as the first vector in R2. So when I multiply this, right, what happened to this? When I multiply the first vector in R2, I get 0. And when I multiply it to the second vector in R2, I get 1. So that means if I apply x to little x, I get 0. And if I apply x to little y, I get little x. Is this better now? All right, so I can now play with this basis and tell you a little bit how this works. When I look at x applied to this gadget here, all the little x will vanish. All the y will be transformed into little x. And I have L minus k of them, so that means I have L minus k times f. I have one less. I have one more x, so that means that I've raised this by 1. Whoops, I'm not going to do twice the same thing because that's boring. If I apply y, that's the opposite. When it acts on the y, I get 0. When it acts on x, I create a y. So I have a L minus k times f little k minus 1. And h works totally differently. H is just, each time I see a little x, I have a factor 1. Each time I see a little y, I have a factor minus 1. And so basically, when I apply it to a basis of that shape, I get a contribution of L plus k minus L minus k. And so that gives me 2k little fk. So that allows me to look at a little graphical representation for, let me do V, too big, V2. Now let's imagine V2, I know it's spanned by this particular element. There we go. H is acting as 0 here, as 2 here, as 4 here, minus 2 on this one, minus 4 on this one. Capital X is moving us in this direction. And capital Y is moving us in the other direction. Okay? So a little graphical representation of that space V2. So what's special? I told you that this basis that my friend found on Wikipedia, and that you can find on Wikipedia too, it's still there, okay? That basis, it is very special. That basis is a basis of eigenvectors for a very particular choice of element here. And it's an element, yeah. And we call those weight vectors. So the Fm are called weight vectors. And they're very special. So in fact, if you study representation theory of compact Lie groups or Lie algebras, you're going to encounter this terminology. It's much more complicated in general. It turns out that SL2 is the very easy case. But in general, things get quite complicated. Any questions so far? Okay, I mean, you sort of know, those of you that just walked in probably don't know you haven't heard what I said earlier, which is that at the end, all of this will not matter. There'll be a second part of the story. But for the moment, you sort of have to play with us. All right, then, so remember this combination, the big question was to find a combination of the spherical harmonic that was invariant under rotation. What does invariant under rotation mean? It means that basically as a representation you obtain a trivial representation. And in fact, what you should obtain is 0. That's the thing we're really looking for. So I'm going to rephrase the question. The question was to find a function, an element of, well, I'm going to cheat a little bit here. I'm going to introduce a piece of notation which many of you have no clue what it means. But I'm going to fix that in a second by not calling it this way. But just in case you know, then you want to find an element of this where h, x, and y all act as 0. All right, so you don't know what that is. I'm going to write down things very differently. So when I look at VL, tensor VL1, say tensor VL2, this is very simple. It's, again, the span of something. Remember that VL1 was the span of little x to the L1 plus K1, y L1 minus K1. I'm just add a 1 there. I'll put the x2 to the L2 plus K2, y2 to the L2 minus K2, and I'm going to ask that K1 be between minus L1 and L1, and K2 be between minus L2 and L2. If you don't know, I mean, this is something you can play with and you can manage. Don't worry about this piece of notation. This is just some abstract general concept that turns out that in this case these two things are equal. So now I can have h act on this, y act on this. How do they act? Same thing as before. When it acts on an x, for example, capital X, when it acts on a little x, it sends them to 0. When it acts on y1, it sends it to x1. When it acts on y2, it sends it to x2. And therefore, this is our representation. It turns out that V of L1 tensor V of L2 is a direct sum of as a representation, this is equal to this. So they're isomorphic. And okay, I'll skip that. And the unique irreducible trivial representation of SL2R and VL tensor VL tensor VL. I can create such a thing by just adding another set of variables. It's very easy. Is spanned by sum M1 plus M2 plus M3 equals 0. Notice one thing. This was what? This was the appropriate F. I'm going to call it L1 K1. This was F of L2 K2. No need for a comma. And because I've put them next to each other, I'm going to put this extra piece there. So this thing is spanned by turns out this is spanned by this. How do you know that this is spanned like this and that works? Well, you have to apply H, X, and Y on this and verify that when you do, you get 0. In fact, there's a better, more easier way using the Casimir, but let's not get there. And what are these numbers? I never told you what these symbols meant, and these are the Wigner 3J symbols, or they're what from mathematicians' perspective is called the Clebsch-Gordan coefficients. And the number, the L1, L2, L3, M1, M2, M3 is the coefficient of x1 to the L1 minus M1, y1 to the L1 minus M1, x2 to the L2 plus M2, y2 to the L2 minus M2 is the coefficient of this in the unit eigenvector of H of eigenvalue 2M3, so that corresponds to that little thing there, in the copy of VL3 and VL1 tensor VL2. I told you just here that if I take the span VL1, VL2, I have in fact an isomorphism with various copies of V's. If L3 is between those two numbers, I have a VL3 somewhere here. I have an element in here that has a particular H eigenvalue. Say if M3 was equal to 0, you'd want the F0. If M3 is equal to 4, you'd like the F2, etc. So there is such an element. Here, that means it can be written as a linear combination of these monomials, and there are coefficients, and you pick up all these numbers. It's very interesting, but it's a rather complicated way to do things. And in fact, that was the first strategy when I tried to approach this problem. And I'll now explain what is the strategy to solve the question. The strategy to solve the question is to learn the full representation theory of SON for any n. And then find the trivial representation in a triple tensor product. And so by that I mean that there exists a notion of weight vectors similar to what I've used this, but more complicated. There's a decomposition like this, so I can also find some coefficients like this. And therefore I have to balance things out very neatly so that, that I get the right answer. And not only that, remember this is very abstract right now. I have to map this to the actual spherical harmonics so that I can have functions to give back to my friend. And I started playing around that route and realized this is actually very bad. And so what does a pure mathematician do when faced with such a situation? Well, first let's recap. So first we looked at polynomials that are homogeneous of degree L. Then what we do is we solve amongst those polynomials those that are harmonic. And three, what we do is we combine to find a function of three sets of variables, invariant under SON. And doing that was the complicated thing. Really, this is simple once you have a finite vector space like this. If you want to solve this equation, this is very easy. You could put it into Maple, for example, apply this with random coefficient. It gives you equations on the coefficients. It's very easy to find out what are the harmonic, what are the spherical harmonics. This was the hard part where we needed representation theory. So let's actually turn this around. All right, where am I? There it is. Notice I have 3 boxes here, right? Let's do this strategy. Let's start by 3, go to 2, and finish with 1. And then everything is so simple. So what is 3? Find an element and polynomials with coefficient of x, y, z. And remember, that here x is really a shorthand for x1 to xn, and y is a shorthand for y1 to yn, and z is a shorthand for z1 to zn. So you want this invariant under rotation. And so, theorem, due to Weyl, there exists a polynomial g, and I'm going to put little x, little y, little z, a, b, c, so 6 variables, no more. I don't need more variables, such that f of capital X, capital Y, capital Z is equal little g of the length of x, the length of y, the length of z square, the dot product of x with y, the dot product of x with z, and the dot product of y with z. Let's say my friend wants this formula in R25. I can have polynomial with 6 variables that actually produce that. Now let's see where are we going with this. After 3, we go to, well, there you go. So this is wrong strategy. After 3, you go to 1, okay? F being homogeneous of degree L, that means that if I look at f of lambda x, mu y, mu z, this is equal lambda mu nu to the L, f of x, y, z. Well, that's the same thing as asking that the little g, remember that little x in our mind should be the same thing as the length square of capital X. So I just put a lambda square here, a mu square here, a nu square there. I'm going to put the lambda mu on the a because a is the dot product of x with y. I'm going to put a lambda nu over there and the mu nu over there. And what I want is that this be equal to lambda mu nu to the L g of little x, y, z, a, b, c. Well, it's a little ugly. But it's a sort of notion of homogeneity. So in fact, it is easy now to find a basis of monomial for example, if I let L equal to, I have to be careful, I don't want to get something too crazy here. L equal 4, then if I choose, for L equal 4, we get one possibility is to look at x squared, y squared, z squared. That's a particular object living in that space. I could look at a squared, b squared, c squared. But I also have things of that nature, x, y, z, a, b, c, for example. And there are objects that are not in there as well. So you can find a bunch of monomials. You'll find a finite dimensional vector space. And now the last step is to solve that equation. But now this is a stupid little calculus problems you could give as soon as you know what partial derivatives is, I could give you this problem, in fact. So number 2, 3, 2. We want to solve this. F is equal to 0. this thing equal to 0, and this thing equal to 0. So it needs to be harmonic in the 3 sets of variables. And notice that if I look at d over dx1, for example, of f of x, y, z, then this is the same thing as applying look at little derivative of little g with respect to little x, but now I differentiate little x with respect to x1. I differentiate little g with respect to little y, but that turns out when I do dy over dx1, that's 0. So I go to this one here. So that object here is just 2x1. That object here is just y1. That derivative here is just z1. So I can do things like that. And then we can obtain. So the upshot is that you easily obtain operators dx that take a polynomial of x, y, z, a, b, c, this set of polynomials to itself, dy, we obtain also a dy and a dz, such that, can easily do that, such that when I look at the Laplacian of f, evaluated x, y, z, this is the same thing as dx of g applied to, as before, the length square, the length square, the length square, x dot y, x dot z, y dot z. And similarly for delta y and delta z. So it's so easy, in fact, that once I've reached that point, I could just program a computer and provide a lot of these invariants that my friend wanted. And notice that just by changing our point of view, I was able to answer that question that appeared very difficult at the beginning. So once we had these functions, we later proved that, in fact, I mean, this was for physics, so we proved that crystallization is harder as you increase the dimension. We also proved various things about the glass transition that led, all of this work led to a new world, if you want, where new hypotheses to try to understand the glass transition had to be tested in higher dimension. There's now a Simons collaboration grant of $10 million for cracking the glass problem. That's the actual title of their grant, is cracking the glass problem. Because, as you're probably not aware, people don't quite understand the glass transition. How does, while we can understand it from the engineering point of view, we don't understand it from the scientific point of view. We don't understand why it happens. And people are trying to crack these problems. While all this representation theory I learned was totally relevant at the end, I did spend a couple of months learning it and digesting it and trying to go further in the representation theory of SON. This was not lost. I was able to reuse that information later. The message basically that I want you to take home is that as a pure mathematician, you don't have to necessarily to approach problems the way that they had been approached in the past, especially if they've been approached by a physicist. And that's also true if they've been approached by other people. That is, you will be able to solve sometimes problems just because you look at one problem in a different way. However, I encourage you to be curious and to learn as much as possible about various parts of mathematics, because you never know what tools you're going to need to use. And I certainly hope that I was able to maybe give you a hint about some of the beautiful tools that exist in mathematics, from representation theory to geometric representation theory and geometric invariant theory. So thank you.
So isn't physics in 3 dimensions? Like, how does it help to have big spheres?
What happened is that there are, when physicists are doing their work, they have to make lots of approximations. They have no choice. They make some simplification. And when they do these simplifications, sometimes there are things that look alike. And very often they jump to the conclusion, oh, there's a correlation here, and therefore this must be the cause. And now what you can do is you look at the same physics if you want in higher dimension. You can run simulations on computers. You can imagine the statistical mechanics. And sometimes these coincidences actually totally disappear when you go in higher dimension. And that tells you that basically the hypothesis that the 2 quantities say were equal was wrong, was flawed. When you go in higher dimension, these identities persist, then you have a good indication that in fact they might have been correct. But of course you're right. The goal is to find out what's happening in 3 dimensions. So this cracking the glass grant, if you want, or this work that an international group is doing, is actually trying to bring from infinite dimension, where apparently everything is solved, to 3 dimension. So that's the thing they're working on.